Okay, welcome back. So, just to remind ourselves, once again, that unfortunately, poor Alfred Wegener's theories were rejected. Womp, womp, womp. And it took many years later, hi, Pony, for evidence to begin to mount. Basically, we had to have technology to help us figure out that, hey, help us figure out that, maybe this guy had a point. But we just needed further evidence, right? He could say that things fit and that there was glacial evidence and all that kind of stuff until he turned blue in the face or until he got an icicle on his mustache. But we needed further technologies to prove it, basically. So turns out back in, as much as the world wars kind of sucked, one nice thing about them was the military was able to develop technologies that allowed geologists to map the ocean floor. Say what you will about the military, I do all the time, but sometimes they can actually provide us with some good stuff. So in 1962, Harry Hess, this other guy, proposed this theory of seafloor spreading. Basically, we have this rising hot mantle, which caused oceanic crust to elevate, which then formed this mid-Atlantic or mid-ocean ridge. And then the seafloor then diverges or pulls away from at said ridge. And then on the other side, the cold, dense seafloor then sinks back into the mantle. Thus, 3 more kinds of evidence were then discovered. So seismologists were able to discover that earthquakes are more so centered at plate boundaries, which indicated motion, right? So all these little red dots here are indicating earthquakes, and that's where a lot of motion and commotion be happening around our planet. So that's one theory. Our next theory is this evidence of magnetic reversal, which was then locked in the oceanic crust. So if you didn't know, our Earth has magnetic poles, one in the north, one in the south. But turns out that our magnetic north and our magnetic south were not always where we currently consider them, meaning that our magnetic north used to be down in the South Pole and our magnetic south used to be up in the North Pole. And we'll learn, if you're in my lab, we'll learn that they wobble, the magnets themselves don't really stay in the same place. And when that switch happens, there's evidence within the Earth's crust to help support this theory. And to be real, like overall, we don't really know the implications of what happens, or we don't know like the products of what happens during this magnetic shift. There is a theory that we are currently at the beginning of a magnetic shift. Fun factsies, I once dated a dude that was a super conspiracy theorist, and one of the reasons I actually got into earth science was so I could get ahead of the curve and like understand what was going on. Don't date conspiracy theorists, y'all. It's not that fun. I mean, it was fine, but whatever. So anyway, there's this evidence within the Earth's crust that can showcase the reversal of this polarity. So this is kind of looking at a very, very simplified cross-section of like the mid-ocean ridge, and the colored lines indicate normally magnetized dikes. So that's when our planet was in a normal magnet era, and these gray stripes indicate reversely magnetized dikes. I'm not a geologist. I don't really fully know like exactly what the evidence was, or like kind of, what exactly they're looking for. I simply know that the evidence is there. And that was another like striking thing about this piece of evidence that was like, oh, okay. Once again, homeboy might have been onto something. And then the third idea is that of radiometric dating. So we've been able to take samples of oceanic crust and we've been able to date them, take them out to dinner, a nice glass of wine. Oh, wait, sorry. No, that's not right. But we can see that the age of the crust increases with the distance from these mid-ocean ridges. So Our scale is over here. Our legend scheme is over here in the top right corner. And the darker red indicates younger crust. And the greener color indicates older crust. So we can see this lovely little line that scooches through the Atlantic Ocean. And that's like a really striking stripe of red, indicating that really, really young crust. Whereas closer to the continents, mainly in the Atlantic Ocean, I think it's the most striking, but like closer to the east coast of the United States or to the west coast of Africa, there's those darker greener colors indicating that older crust. It's not, I mean, you can kind of see it in the southern Pacific Ocean, but you know, the west coast of America, I mean, it's not as like, I don't know, striking, I guess. I can't think of any other word at the moment, but we're on a different sort of plate boundary here. So the mid-ocean ridge for the Pacific Ocean is a bit more south. It's not going like straight through the middle of that ocean basin, which is why it's not as like pretty, quote unquote, of an example. So this was actually a quick video, but when we come back, we'll talk about the types of plate boundaries. But what I want you to do before I let you skedoodly on to the other video is consider the first thing that comes to mind when you hear these words. Think about what comes to mind when you hear the word convergence. What comes to mind? What do you think of when you hear that word convergence? Divergence. What comes to mind when you hear that word? And then lastly, transform. What comes to mind when you hear the word transform? And when we come back, I'll give you the solutions to what exactly those mean. Thank you so much for watching. Oh wait, hang on, sidebar. Did you know that on my leg, I have tattooed yellowfin tuna? I have 2 little yellowfin tuna that are kind of hanging out on my knee. I have a whole leg sleeve going on, and yellowfin tuna are indeed involved within that leg sleeve. So, side note.